Right. So this is a sort of a follow-on to last month's meetup. Probably triggered more by the questions after the presentation more than the presentation itself. So I thought we'd cover off two topics here. One is just finish off that question about mains earthing, and then talk about the question of, with inputs and outputs and power supplies, which ones do I bond together and which ones don't I need to, etc. So, but the underlying theme of this is to answer that question is to actually be able to show you how to actually work it out for yourself. So, because every application will be different, so you sort of have to have the basic skills to actually work each one out for yourself. So that's really what the underlying theme of this is. And what I'll do, I'll actually do this more in the mains earthing side. Not that I'm really focused on mains earthing. It's actually using that as an example to show you how you go about doing this. So, so the question is about bonding. And when I say power supply, it could be, a 12-volt power supply or a 5-volt power supply for a Pi, or the 220-volt, 240-volt input. They're all power supplies. and I deliberately separate this into two functions here. One you worry about is will the circuit actually function, and the second side is safety. And quite often, I think we have these discussions about bonding. We're jumping between these two, and we need to sort of separate them out. And I think what you'll see is, in many cases, you actually don't need to bond them together for function, but you might do for safety reasons. So we'll actually look at those two aspects. So starting on looking at mains earthing, I thought I'd start off with an example of a sort of a portable generator, and let's pull out the rule book and just check whether it's properly earthed or not. So, it's got an earth wire, so we can see a green-yellow earth wire, and it's connected to an earth stake, so that's pretty good. And it's got the right type of clamp on it, so we're going well here. And yes, it's actually inserted into some soil, so looking pretty good. Well, what else do we want? Maybe a bit of continuity would help. So the theme of this is I'm using the word show me the circuit. So it's like, let's just start trying to draw out the circuit. So to start with, so this is a bit more of good practice rather than showing circuitry. So we talk about bringing an earth from a mains earth into a piece of equipment, and we talk about bond it to the metal so that you end up with a protective earth. So there's a typical case of a machine I've actually built: a metal stud, a bolt and nut, and the next thing is don't forget to do all the moving panels. Don't rely on the hinges for continuity. So it's a separate wire to each panel, and you'll see that on appliances like washing machines, etc., with removable panels. There'll be a wire to each metal panel. So the concept is you take a stud and put a washer on it, put a crimp connector with a wire in it, another washer, a nut, and you can stack them up. And then, so you see on the left-hand side, you can actually put multiple terminals. You don't need a washer and nut between each one. But the key and the important thing here is to use a star washer, something that will actually cut through either the paint on the appliance or the metal panel, and also cut through the oxide layer on any connector and terminal. So to come back to the question about show me the circuit, I thought we might just start having a look at this sort of thing. So here's a classic case: street transformer down at the end of the street. High voltage coming in, say 11 kV. There might be a circuit breaker or a fuse in the power authority might have. Cable comes down the street to your switchboard. You've got circuit breakers in your switchboard. The neutral is actually connected to earth at multiple points, and including in your own switchboard. There's a cross connection between the neutral and the earth. And then you might probably have an RCD or and I don't, in the UK, I don't know what you'd now call them, ELCBs or safety switches, or they go under a number of different names. And here's the earth down the bottom, the earth wire going to the metal panel. There's the black dots are representation of a stud connecting to the metalwork. And so the theme will be, let's start figuring out where the current flows and where it doesn't flow, and that's how you go about answering this fundamental question about bonding. So, okay, so let's have a look at the circuit. So there's a typical load on the right-hand side. So the current flows from the street transformer all the way down the street, through your switchboard, down the cable to the equipment, through the primary of the transformer, and back around. And you'll see in the RCD, there's current flowing one way in the active and in the reverse in the neutral. The total magnetic field from that is zero, so the RCD doesn't see a fault. It's quite happy. And then in blue, I've got the current in the secondary of the power supply. And that's the important thing is the electrons flowing around that circuit are quite different to the ones on the primary. So that, transformer is an isolated supply. And the two circuits are absolutely independent. So on the left-hand side, you can see the mains is earthed. One side of the main system is earthed. In my diagram here, the secondary is not. And it's quite happy. There's absolutely nothing wrong with that. So now, what we now do is say, okay, well, let's have a look at some fault conditions. So here's an active is shorted out to the metalwork, and you can see now where the current flows in. I'm still down the active, down through the short circuit to the metalwork and back along the earth wire. And in this condition, the RCD is unbalanced, and so it would be trying to actually cause a trip and trip the circuit breaker. So that's the sort of thing we need to do is draw these sorts of circuits out to figure out the question is where is the current flowing and what connections do I need? So from a safety point of view, this earth wire was bonded to the metalwork of the hardware. It's not there for the function of go back a page here. The function of the equipment is this red circuit. It's the earth bond does nothing. There's no current flowing in this earth bond wire when the equipment's functioning normally. So separating that question right at the start where we said, look at the function of equipment versus the safety of it. You don't need the earth bond there for function, but you do certainly need it there for safety. Another thing we need to think about is the type of fault. So here, going back a page, here I'm doing an active to earth fault, which is probably the most common type of fault you get. And here's an active to neutral fault where the transformer primary's failed or something like that. But you'll see that in this condition, the current still flows down the active and back down the neutral, and nothing in the earth wire. So to the RCD, there's nothing wrong. There's a balance still there. The currents will be very high, but in terms of where's the current flowing, it's actually still flowing through the active and neutral. And what you get is not the RCD tripping, but the current overload, circuit breaker or fuse will trip. So you do these sorts of scenarios to work out where the current flows. So what have we learned here? Well, we've learned that a protective earth provides a circuit back when the active touches the metalwork. It prevents the metalwork becoming live. Protective earth's got nothing, is not involved when you've got a phase to neutral fault. That just looks like a massive overload. And the other thing is, coming right back here to this concept of a stud, is if you put one, like I've done here, one connection, you can use that and then and like in this diagram, multiple connections out to all the panels and everything. So you sort of have one central point that you call your protective earth. And you can do the same sort of thing on the secondary of a power supply, like if you connect the 12 volt negative of a power supply, you can create this concept of an earthing point. So coming back, here's the typical load again on the secondary side. Nothing wrong there. But let's put a hardware fault on the secondary side. We'll put a short circuit. It's a bit like what John had with the power supply, 12 volts out, and you put a dead short across the 12 volt output. And the important thing here is that on the primary side, the current still flows through the active and the neutral. And even if I put a short circuit on the secondary to say to the metalwork, there's no current flowing in the active. There's no current flowing at all, but there's no current flowing in the earth from the 240 volt side. So in this case, we've got a secondary side that's floating, and you can put an earth fault on one side and nothing will happen. It will still keep functioning. There's no current flowing in that through that unexpected connection. The problem with a floating system is when you get a fault, there's nothing wrong. It keeps working until you get a second fault. And I've had systems like this in machines, and trying to find the two faults, because you don't see a problem until you actually get two faults. And trying to find two independent faults in two completely different parts of a machine can be really hard work. But the important thing here is, here we've got some sort of fault on the secondary, and again, the current in the primary is still staying in the active and the neutral. There's no current flowing in this earth wire on the primary side, on the 240 volt side. So that's a theme you'll start to see. As soon as you put some sort of isolation in, the primary side or the upstream side of that isolator, it doesn't see any unbalance at all, and never will. So a system on the secondary side where you've got it floating, you can have faults and they have very little effect on the primary. So one of the things you can do is not for circuit function, but for fault finding. Take the 12 volt supply, like John's 12 volt DC, and connect the 12 volt negative to the metalwork. And what that does is has the advantage is when you have a fault, the first fault, your circuit protection, like the power supply, might shut down through its current limiting, or you put a circuit breaker or a fuse and it'll blow the breaker, blow the fuse. So here's a secondary with a bond to the earth, and I've just so happened taken it to the same as the mains point. Current flows in the secondary quite happily. Note there's no current flowing in this earth wire at all. As soon as I put a fault on, an earth fault on there, so now that the 12 volt positives touch the sort of in John's case the metal gutter of the house, and that's taken there's a wire's been rubbed through and now got a short circuit on an LED. You'll get a current flow, but again you can see that it's in the secondary side here in all these blue wires, the blue arrows. You can see where the current's going to flow, and your circuit protection can take care of that and blow a fuse, etc. But note here the current's flowing back through the metalwork of the building or the cabinet at this point, back up to the negative of the power supply. It doesn't go back to the 240 volt side. It's got nothing to do with it. There's no physical circuit to be had there. And so this is the fundamentals of trying to figure out your connections that you make. Do I make this connection or not? Because you really want to do is draw out these circuits, and that's really the theme of this. So what have we learned here? That when you use an isolator, and when I'm talking about an isolator, I could be talking about a transformer, I could be talking about an optocoupler, I could be talking about a relay. It's really full isolation between two systems. Two electrical systems are truly independent. so if you get faults on the secondary side, all they'll do is look like normal load or an overload on the primary. You know, you will not get any earth current flowing back into the primary side. And we use the term, you know, you hear the word galvanic connection. So this is not a non-galvanic, because there's no metallic connection between the two systems. You know, in this case, it's actually the primary winding here. The electrons in the primary are creating a magnetic field, and the magnetic field is coupled to the secondary coil and creates current there. There's no metallic connection between the two. So we'll come across and we'll look at the same concept now on, say, the input to a pi, or you know, input or output to a pi. And we'll initially look at isolated inputs and outputs. So again, let's show me the circuit. So I've drawn here, I'm actually going to, while this applies to inputs and outputs, I'm actually just going to draw this as examples will only be outputs. So on the left-hand side, I've got a 5-volt power supply, you know, a little plug pack or something similar. 5 volts goes to the pi. It could be through the USB connector. Comes down through, the current flows through the 5 volt to 3 volt regulator that's on board the pi, feeds the ARM chip. Current flows out through a GPIO pin. So when you turn on the IO, the code, the current will flow through the LED of an opto and back around back to the power supply. Now you could connect this the negative of this LED back to the negative pin on the GPIO header. Either way, it doesn't matter. That's still the current flow. So that's the primary side. On the secondary side, now we've got light appearing at this transistor. We'll get current flowing on the right-hand side. We've got a 12-volt power supply, and I've deliberately picked a different voltage here. So it could be 12 or 24, or if it has an AC system, you know, it could be anything. So current flows around through the LED, through the opto coupler, the transistor and the opto, and around there, and that circuit is quite independent. So if I show them both together, you can see that there's actually no current flowing. But from a function point of view, these two circuits are quite independent of each other. And again, there's no need to connect the negative of the 12 volt to the negative of the 5 volt. They will work quite happily independently. So what have we learned here? So with isolated inputs and outputs, to make it function, and I underline the word function, there's no need to connect the negatives of each power supply together. If you do connect them together, it actually makes no difference to the function of the circuit. But you might want to connect the negative of the power supplies for a safety reason. So I'm just coming back here. What I quite often do is so I've got a pi in an enclosure with a 5 volt supply to it, and the 5 volt doesn't leave the enclosure. So I don't have much exposure from a safety point of view on that. But what I do extend outside is the wiring to this LED, and I'll have the 12 or 24 volt supply, you know, maybe running a few meters or, you know, hundreds of meters around a factory. Now, in that case, someone could actually, you know, quite independently, someone could accidentally drop a 240 volt wire on that circuitry. So what I'll quite often do here is I'll connect the negative of this 12 volt power supply to the mains earth, to 0 volt. And so what I've done is, if 240 volt was to be dropped on this, I'd probably, insulation, the 12 volt insulation would probably break down on that wire. But I've provided a circuit, and you know, the opto coupler wouldn't like it, and it would fail and short circuit. But what I've done is created a safety path for that external voltage to go back to earth. So what I've said here is I quite often connect the negative of the 24 volt power supply that feeds the loads to the metalwork of the cabinet. but it's for safety, not for function. And I deliberately don't connect the 5-volt supply of the Pi because I've got here a, oops, get back. You know, I've got this thing isolated. I don't want stray currents, you know, coming through and taking out the Pi. So I deliberately don't connect the 5-volt power supply to earth because the whole point of an optocoupled or an isolated system between a Pi and the field wiring is to stop unexpected currents flowing through the Pi and taking it out. So my I/O boards that I've got, my optocoupled I/O boards I make, they're there particularly to stop these stray currents, unexpected currents. So let's go the other way and look at the alternative where there is a connection between the field wiring and the Pi. So again, you get sick of me by the end of this. Have a look at the circuit. So what I've drawn here is the typical open collector driver, and Richard is famous for using these for. And I've just drawn I think they come in what four transistors per package or something of that order. So the idea is that you put in 3.3 volts on the input of this device. All the transistor emitters are all commoned up to a connection, and the idea is that you turn on 3.3 volts and you turn on a load that could be, say, a half an amp or something like that. So let's start drawing the circuit in. So on the primary side, to make this work, you need to connect the emitters, common emitter, back to the negative of this power supply, so you get this current flow in through the base of the transistor. This blue dot could be something nothing more complex than just a resistor, a current limiting resistor for the base of the transistor. So you end up with this. This is the circuit for the primary side. Switch over and have a look at the secondary side. Much the same as with the optocoupler. Current flows in through the lead, through the transistor. The only thing I'd make a point here is you'll see that it's the same point back here. It's the same wire. It shares the same wire on this open collector driver. So if we draw both circuits together, you'll see we've actually got a common connection here. And if we display the current flows, so again, what we've got is there are two separate current flows here, but they happen to share the same physical connection pin on this open collector driver. So here, to make it function, we had to connect on the left-hand side the negative of this 5-volt supply to the negative of the 12-volt supply. So this is a function issue, not a safety issue. Excuse me a second. So to make it function, you need to make a connection. However, the currents are quite separate from each other. So in this area where you've actually got a galvanic connection, the control current and the load current pass through the same pin, and it's for that reason you need to connect the supplies together. But there is no current flow. If you look on the left-hand side with the red, the current flowing in the shown in red, there's no current flowing between the power supplies. They're just sharing a connection. So the third area is power supplies, and there are effectively two types of power supplies. The isolated type, which could be a classic 240 volt 50 hertz transformer. It could be a switch mode power supply like the one that John had. That will actually be taking 240 volts in, converting it to DC, something like 200-300 volts DC, switching that at high frequency through a very small transformer, and then rectifying it back to 12 or 24 volt DC. but they are isolated. And so here I've drawn, and this actually happens to be a power over Ethernet power supply I use. It's got 4 connections, and the input is quite separate to the output. So if you run them like a 240 volt to 12 volt power supply, you make no connection between both sides, and it'll function quite happily. You can put a wire between them if you wanted to, but it would actually not change the function of the circuit. And then you come back to these little switching pulse width modulated switching regulators, where again they've got 2 connections, 4 connections, 2 on the left hand side, plus in and negative in, and plus out and negative out, and you connect them up just like this, 24, 12 volt on the input, and you get 5, so you adjust them for 5 volts on the output, and they quite happily work. But what you probably don't realise is, drawn here, in this circuit board, in the track of the circuit board, it's actually a connection. They are actually one and the same. The negative in and the negative out are actually one and the same connection. So I've drawn that sort of in the circuit diagram as a dotted line. So you can put a connection like that in your circuit board, and it'll make absolutely no difference. In fact, you can go further and actually take away that connection and just make it a three wire connection to these power supplies, and they'll work quite happily. So with that, anybody have any questions?
Tony, thanks for that, because I've only took up electronics not so long ago, and this kind of stuff was really, for me, I mean, I don't know about everyone else, but for me it was really, really informative, and it kind of taught me a little bit about how current moves and stuff like that. I sound like a bit of a novice, but I've already learned so much from you guys already in one sitting, so thank you for that. I really appreciate it. Thank you.
That's all right. I mean, I've had years of actually letting the smoke out of circuits. Don't worry. Experience here.
Well, we're still alive, and that's a good sign. So
yeah.
That seems to be the definition of a. It seemed to me that power supply designers were used to things bursting into flames, and yeah. I've got a question actually, but the first thing that I'll say actually is that the 12 volt supply, the one that took the 240 volts and took that down to 12 volts, I was actually surprised to find that the negative output, because you've sort of suggested there that would be isolated, and that's kind of what I was expecting as well. And actually, when I measured it, when it wasn't plugged in, there wasn't a connection between the 12 volt or the ground to earth. But when I plugged it in, when I said that one of the wires melted, it was actually where I connected the 12 volt wire to actual ground, mains ground, and that's when all the current went through to ground. And actually, when I looked at it, when you switched the power supply on, it somehow connected the ground on the 12 volt side to the actual earth, mains ground. So I was quite surprised by that.
Okay.
Yeah. I have a large scale example. I was in Brazil as a volunteer working on a project, and in Brazil they have a 220 volt power source and it's center tapped at earth, so that you can get either two 110 circuits or 220 circuit. And in the project, a lot of the lights were either bright or very dim. And also various other equipment was burning out. So I measured the voltages, and we had a 90 and 130 volt. So I investigated and I looked at the earthing, which was done by a wire wrapped round the rebar of a concrete column, and the column was quite hot. So I gathered that what had happened was that somewhere in the shanty town surrounding, someone had earthed the wrong lead. So that we were doing a lot of electrical global warming. Anyway, I disconnected that and it was all right.
That's when I was showing that circuit of a floating output with two earth bolts. That's exactly what that is.
Yeah.
And to find them is like near impossible because they can be huge distances apart.
Yeah. Had the difference been smaller, I might not have twigged it.
Yeah, exactly.
Yeah, I mean, again, that was one of the things I realised was that, you know, with low voltages, I kind of realised that you could, if you had a long enough run of wire, if it wasn't sort of extremely thick wire, then if you short it out, you weren't guaranteed to blow the fuse. It was, you know, you could still get large currents flowing that would just heat bits of wire up.
Yeah.
So one of the things you need to do, both, you know, as I say, because I'm also a licensed electrician. Part of the standard there is actually to calculate the fault current and guarantee that it's going to be high enough to actually cause the protection to trip. Because long lengths of thin wire actually is current limiters. So you're quite often looking for sort of 10 times the difference between, you know, the fault current should be something like 10 times the rated current of the circuit to get those protection to work fast. You're looking for, you know, large differences.
So Tony, when you've got a non-galvanic circuit in a factory and you've got some piece of thin wire, maybe a comms lead running for a long way, presumably you run a protective earth alongside that, but where do you choose to bond it to the comms lead?
You don't. Well, okay. So the classic case is, I had this years ago. A PC in one building, and this was in a bus depot. So it was a PC in one building, and then 300-400 meters away was a field sensing unit was, you know, in another building, and they had them galvanically connected together. It's just RS-232. Like every week, the thing was blowing up. So the issue was to put some optocouplers in it and actually isolate it. The advantage of Ethernet, by the way, is it's got transformers on each end in the equipment, and there's your 1,000-volt protection. So you quite often don't need to actually run a protective earth along the comms lead. You just run, say, twisted pairs or a fibre optic cable or or whatever it might be, RS-485, and not worried about putting an earth wire. If you're really worried about damage, physical damage, something cutting the wire and dropping mains on it, you might be thinking more like going for a screen cable, not to actually provide a screen, a signal screen to the wiring, but to say that any external voltage is actually going to hit the earth before it gets to the signal wires, and I'm going to have an earth bolt. I'm not going to get high voltage or 240 volts on my field wiring. So you do it from a mechanical. You think of it mechanically in terms of which sequence is voltage going to get onto something. but it's not there. It's not there for a screen itself. You know.
Okay. Oh, thanks for that.
Tony, something I remember from a long time ago was people talking about ground loops, and particularly with sort of 1980s sort of hi-fis. You know, you'd get sort of hum appearing on your speakers because you'd got a ground loop in there. Is a ground loop something that people sort of worry about these days?
Yeah, absolutely. It hasn't gone away. In fact, I had when I was at university, I had a Christmas holiday job at a TV studio looking for earth loops. I'll show my age. They'd done the conversion to colour and thrown all the coax cables in real quick. Of course, the screen was connected at both ends, and there were earth loops everywhere. That problem hasn't gone away. Now with digital, it's certainly a lot. You know, you don't get the sort of the background hum issue anymore, but you certainly do. You still need to be careful of it. So you get it with things like you know, servo motors. You know, where you got high-speed encoders. You might have you know still a digital circuit, but if you get a bit of noise on an encoder circuit, it's enough to upset the drive. So I've been putting a large number of servos in lately in the last year or so. Every one of them I'm very careful about not forming up earth loops. So you know, things like the screen is only connected at one end and it's deliberately open circuit at the other.
Right.
And I very carefully think out which end I'm going to earth, not just arbitrarily say one end or the other. It's a deliberate attempt to you know, to control that, if you like.
Under what circumstances is it best to earth anywhere other than near your star point, near the supply end?
Probably not. I tend to always do it that way, back to the supply. Just by my habit is to go to the supply end always. It's probably more by convention than necessary, but you know, fault finding is, you know, having some standards in the way you do things helps with fault finding. You know, I know where to expect to find things, and I know where to go test them, etc. So you know, a lot of things are not necessarily, you know, even function of safety. It's like you know, repair time and downtime.
Yeah. Do you think we might be safe with just sort of following a star point rule blindly, or is it worth thinking through each circuit?
Oh no, I sit down and think through each circuit.
Okay.
The thing you've got to be careful. I'm sort of surprised what John was saying about this power supply. You know, it would seem that there's something going on there that's unexpected. That's probably the more important issue, is to understand these sort of things. You know, are they truly isolated? Is it got some leakage in it somewhere? So it's tapped somewhere. Unfortunately, it's got a fault in it or something. I'm not saying, John, I'm not saying it has got a fault, but you know, it's about understanding these things. That's probably the most important thing.
Well, I mean, it's something that I would say to other people to be aware of, is that you know, because I expected the output to be floating, but it's not. Because you know, I thought, well, if I connect the 12 volt to ground, then I could have minus 12 volts on the other side. But you know, you can't. If you connect 12 volts to ground, then you'll get a piece of wire that sort of starts to melt, or a fuse blown or something.
The other thing is, just as an aside, you know, we always talk about putting the negative 12 volts, the negative of say 12 volt to earth, you know, just as by convention. there's nothing to stop you putting the positive 12 to earth. There's nothing magic about the negative side. And so, in fact, in a telephone, the old analog telephone system, which runs at about 48 volts, the positive actually is earth in the exchange. And so it's actually negative 48 volts is delivered to your house, not positive 48.
I think some cars used to have a different earth, didn't they? Some were positive earth and some negative.
Yeah. And so it's not that one's better than the other or one's safer than the other. It's more convention. You roll up and say, "Oh, I'm going to have to diagnose a fault in this car," and it throws you because it's unexpected. It's different. And the same applies to be it 12 volts for an LED circuit or whatever. If it's outside the convention, it's also like negative switching. Japanese cars, I don't know what they are today, but historically, things like the light switches, etc., are actually switching the negative of the headlights, not switching a positive to the headlight. So it was always a it would throw, and we still see this in machinery. The Japanese still tend to switch the negatives of solenoids and hydraulic circuits and all that. And it does take you a while to get your head around. Oh, hang on, I'm looking at something which is not, which I would say is not conventional. There's nothing wrong with it, but it just gets me every time.
Yeah, one thing is, if you're piggybacking two 12-volt power supplies, you need to make sure that one of them isn't earthed.
Yeah.
Otherwise, you won't get your 24 volts.
Straying towards a question, thank you again for the presentation, Tony. Straying towards a question I was thinking of recently that perhaps is a good time to float. A very simple circuit, in fact, that I have at home is I have an LED strip in my bedroom, and it's behind the headboard of my bed. At the moment, it's plugged in at one side. I have an extension that can be reached from one side of the bed. And I was wondering, is it a terrible idea as a poor man's staircase switch to put a second 12-volt power supply plugged in at the other side of the bed that's soldered to the other end of the LED strip, and then you can turn on either supply and so from either side, and it would do it?
There's probably nothing wrong with that. The only thing you got to check for, so the two will never be exactly the same voltage.
Right.
So say that one was 12 and one was 13 volts or something like that. You turn the first one on at 12, it will run everything. You switch the second one on, it'll probably try and run everything, but the first one will probably switch off at that point.
Yeah.
So you've got to be careful on load if you're doing it for load sharing.
Now the idea is either one would power it. It's like a step. Obviously, I don't want it to blow up or anything if I do accidentally flip both switches. But
yeah. So give you an example. I'm just trying to. I've got it here. So I've got a PoE on top of a Pi. I've got my own hat that I put a PoE power supply on.
Mm-hmm.
Oh, actually, I tell you, even the those 24 volt to 12 volt little in the presentation, these things like this. So I've got some hats that I because industrial is typical 24 volt DC. So I can always find 24 volt DC in a machine. So I put one of these power supplies on, step it down to 5, and away goes the Pi. I can actually plug in a 5 volt power pack into one of those. So I've got two different power supplies going into the Pi. This one will just switch off. But, whichever's got the highest voltage takes over. So that's quite common.
Okay.
There's nothing unsafe with that. What you do need to be careful of is ask the question, what happens with a power? Just it's a general question. I've got a power supply. I've got the primary turned off. There's nothing, and I apply voltage to the secondary.
Well,
what does it do?
Yeah.
Now, most of them have actually got something like effectively got a diode in the output or something similar, or the equivalent of, and they just do nothing. They're fine. If it's some odd bod power supply where it starts drawing a large amount of current, then you've got a problem. But in general, well, it doesn't smoke too much. You'll be right.
So it's an AliExpress power supply. Try it and find out. Is the
That's the one.
yeah, everyone's
And
favorite.
buy two just in case.
Yeah, I already bought 3 and 2 of them didn't work. So
One thing you could consider is just looking at the way toggle light switches work. You know, when you've got an upstairs and a downstairs light switch for.
Well, that's what I meant by staircase switches. Yeah, and that is, don't get me wrong, that's absolutely the proper way to do this. I accept that. But at the moment, I do it easily because I just have an extension screwed into the bedside table on each side. And for my phone charger and everything, it's got switches on the extension. So I switch it on the main side. And, you know, so that's why the easiest way for me is just to plug in a second power supply on the other side rather than doing switches in DC.
The switching things, you know, the thing where you have a sort of light switch downstairs and upstairs, switching a light on and off. That was an interesting thing for me when I looked into that, because I would assume that the way they do that is to connect the live and neutral to a switch at both ends of you know, both switches, and then have, you know, when you flip one switch it goes live and the other one goes neutral. But actually they did that up until about 1930, I think, and then it was made illegal. And I can't remember. I mean, Tony can probably tell you what the different conventions are for these things. I think there's names for how they do this.
Yes,
Are you saying Tony was alive in 1930?
Yeah, the old way, you could end up with both sides of your lights
being live. Yes. Yeah.
It makes it dangerous changing a bulb.
Yeah, and I think that's why they made it. As I say, they made that illegal in about 1930. I can't remember what they called that switching, but
yeah, I moved into a house with the old system, and I couldn't understand why the fuse kept going until I checked it.
Well, it's a good job you didn't poke your finger in the lights, you know.
Well,
socket,
because I put a new switch on using the new convention.
That would do it.
Yeah.
Of course, the answer in this kind of group is actually why are you not using a smart switch of some sort?
Too newfangled.
Like, I do have a project underway. I want to use a Pi 0W to fade them up ahead of my alarm in the morning, right? And PWM it kind of for half an hour or something coming up. And I was going to do MQTT or something. I haven't got as far as the software really yet.
I ought to mention that I've got a power supply from AliExpress, which is used for charging batteries, and they specifically say not to let the battery backfeed into the output. So evidently there are some kinds of PSU that are harmed by that. And so what you could do perhaps is put a diode in each of the positive feeds, so that but on the other hand, if it were me, I might find myself getting annoyed at switching the lights off only to find they stay on and I have to roll over to the far side of the bed.
Well, that's, again, in principle, they should always. But yeah, you're right. It won't be. You would have to make sure both are off to be off.
And that is a fat diode if you're going to be pulling probably a good few amps through it.
Yeah, it's about 1.3 amps.
Oh,
it's not quite wide enough a bed to need 15 meters of LED strip going across it.
Yeah.
I didn't know if it went backwards and forwards and round the bed a few times.
No, just one.
So with model power supplies, you see that with long LED strips of where you might need. You got a really long strip of pulse modulated chips. You need to put power supplies or model power supplies and then spread them along the thing. One technique is to separate the positive, progressively separate it along, so each power supply is only feeding a couple of meters or whatever. And another method is actually to put them in parallel, to put the power supplies effectively in parallel. But to get them to load share, you need them to have a bit of droop so that they might drop slightly in voltage as the load comes on. And normally in a power supply, you think that's actually a poorly designed power supply, but actually droop actually works to your advantage. They will naturally load share, and in fact, that's how in the power generation industry, power stations which could be hundreds of kilometres apart can actually load share because they actually put in about 4% droop, and they just naturally will all hit full load together. But you can use that to your advantage in some instances.
Gary, did you have a question?
Yeah, I was just going to say something to Peter actually. Have you looked at the Sonoff power switches?
The what power switches?
They're called Sonoff. You can buy them from our favourite Chinese website that we've all been talking about tonight. It's an ESP8266 that you can drive a 240 volt power supply on and off.
It's a Tasmotor software, isn't it?
Well, they don't come with Tasmotor. You have to
you flash it with it. Yeah.
You open it up and then you have to solder some pins into it, and then you can program it. And then you can use your phone or your computer,
right,
connect it to the network, and you can set alarms and all that kind of stuff with Tasmotor. Might be safer. I don't know.
Yeah, it's something. I mean, firstly, probably no alien concept to everyone here. I'm not doing it because I think I can do better than the factory. I'm doing it because it's a project, partly, and partly because as well, I want it to fade up. And presumably, if this thing is switching mains, it's likely to be a relay or something, and not going to PWM. Correct me if I'm wrong. So it's that's partly it. The key is to fade up rather than just turn on. Yeah, I could just use a relay and a timer to turn on. That would be easy. So it's partly that I want to fade up and I want to have the control software and so on. And partly,
indeed. I mean, I was just going to say. I mean, you could actually you could write an ESP32 or an Arduino bit of code that can actually drive that.
Yep.
So,
totally could. The reason I've opted for a Pi is there's a Pi there already.
Yeah.
So it's literally already there. Secondly, things like I now don't have to faff around with real-time control because it's already got it on the Pi. It's on my network. It's on my internet. I can just MQTT and say 7:20 a.m. and it will do it at the right time. I don't have to worry about the extra of making sure it's on time. And I know that's also possible with ESPs and stuff, but it's just, it comes naturally. I can write it in Python. I can easily expand the capability. Another reason to do it separately myself is that I want to, and I've got the PCB coming, hopefully for this, have a PCB wherein I can switch. So I've designed a PCB where it generates a pulse width modulated signal with a 555 circuit. And it takes a PWM signal in at 3.3 volts from the Pi, and there's a switch on the top which chooses which of them goes into the MOSFET driver, and then you also have a rotary pot on the top, so you can switch between automatic mode or manual mode, and in manual mode there's a knob right next to it just for standard dimming.
Wow.
So
you know what? I'm amazed. Yeah. I'm amazed actually that there are so many. This under the guise of a Raspberry Pi meetup. There's so many people with so much electronics clout. I'm hearing all different amounts of experience and stories, and I love it. And yeah, it's my first ever one, so happy to be here, guys. Yeah, it's lovely to meet you. So thank you. Yeah. Cheers.
Likewise.
Pleasure.
Can I ask a totally unrelated question? Has anyone used a Raspberry Pi for Zooming? And if so, what model?
Is anyone using it now?
Silence.
I think there was talk on a previous meeting. People had quite a bit of a challenge with it.
Yeah.
So, yeah, I'm not sure.
I just wondered whether the latest ones were fast enough.
Shouldn't be
I
far
don't
off.
think it's necessarily speed. It's going to be down to the correct software that can actually do it, whether it works on it.
Yeah, I don't think there is any software for Zoom on the Pi. I guess you'd have to emulate it, and that would be really slow. Unless someone's written a native version, and I doubt they've done that as well. Yeah, maybe later, but not to my knowledge.
Okay.
It's quite specific now.
You can run it in Chrome or something. I think I was trying to run Spotify as well on a Raspberry Pi, and you needed to run it in Chrome. I think it could work
You
like
have a
that.
question? You have a
One of
question for Tony?
the limitations on the Pi is the codecs available. So only very specific codecs are available in hardware, and everything else is software. So you'll find some things can benefit from hardware acceleration and work really well, and other things don't. Like I think the YouTube kind of 4K encoding, not a hope that you'll get that working on a Pi. It just doesn't support it. Whereas if you've got, I think it's H.264 or 5 encoding, I can't remember which is off the top of my head now. I lose track, but that tends to that has some built-in hardware acceleration. But I think it's there's only one particular codec that supports 4K in hardware.
Yeah, thank you.
So Tony, I had a question for you. I think we were talking at one point about a project I want to do where you have a 24 volts coming in. Then I also need a 12 volt and a 5 volt. So I've got a 24 volt device, a 12 volt device, and a 5 volt out of the Pi itself. So I was just wondering, is there a way to make sure that the Pi always gets as much power as it needs? So if I just start overloading the circuit and I start voltages dropping off, is the 5 volt going to be quite solid power, or do I have to worry about being flaky? If I start drawing, say, too much 24 volt, 24 volt device starts drawing too much current. Does that mean my 5 volt Pi is going to crash? Or is there some way of Pi stays alive?
So in principle, you'd have like a 240 volt to 5 volt supply, 240 volt to 12 volt supply, and a 240 to 24 volt supply.
No. So what I was thinking was I just want one 24 volt supply coming in. So go to 220 to 24 volt, and then from 24 volt DC inside my case, I'll just use buck converters to convert down to 12 volt and 5 volt.
Okay, so
I think you'd have to draw so much current that the 24 volts is going below 5 volts before the Pi would collapse.
Yeah. So
and then you would have a serious fire.
Yeah. So the idea of taking a buck regulator, it only needs about 2 volts across it, so it probably will work all the way down to 7 volts, but it'll still be putting 5 volts out. So the question would be, you've got some other serious overload on your 24 volt power supply if it's dropped from 24 all the way down to 7.
Right.
So I think as long as your load on your 24 volt is reasonable, so your 24 volt could be hitting current limit and starting to drop to say 21 volts or 20 volts, which it shouldn't be doing that because you've probably got too much load on it. But the Pi will still keep working quite happily. So what I would do is I'd take the 24 in, and then I'd take a 24 to 5 and a 24 to 12, take the next steps down. I wouldn't chain the 24 to 12 and then the 12 to 5.
Yeah, I guess that was the other question I had. You're better off having 2 buck converters in a row.
Well, the reason is that the 24 to 12 is going to have to take the current for the 5 volts load as well, and you're unnecessarily loading up that center power supply. And if you had them all in series,
I think I recognise the one that Tony showed on his slides, and that's if it's the one I'm thinking of, it takes up to 40 volts in, and it'll do two amps, I think. I'm not sure whether that's 2 amps in or 2 amps out. One of the nice things about those DC to DC converters is that you can actually get more current out than you put into the things. So if you're going from 24 volts to 5 volts, then you've got sort of up to 4 to 5 times as much current.
Yeah.
Yeah, and how do you choose one of those? So I bought some cheap ones that I quite like. The one of the features is you can adjust the voltage via pot.
Yeah, which that one that Tony's just showing now has got that POS, that's a multi-term POS on there.
Yeah, but this one you can also you also have selections on the back, and you can just solder the voltages you want. So they have some selectable resistors, which I think is quite a nice feature.
So I adjust these things up to about 5.2 volts because you've got a little bit of wiring downstream, and the Pi, I think there's a sort of, I wouldn't say a fault, but it's just a design feature in a Pi that it tends to throw up an under voltage alarm at right on 5 volts. So the regulator on a Pi, the 5 volt 3.3 can take a little bit more than 5 volts.
I think the fuse drops quite a bit, doesn't it?
I go in through the GPIO pins because I've made myself hat, so I don't go in through the USB micro USB connector. I go in through the GPIO pins, bypass all that, and I don't worry about fuse or no fuse on a Pi. If the Pi needs a fuse to operate, there's something seriously wrong with the Pi.
Yeah.
What you do though, I quite often do is in my industrial I/O boards, my MOSFET switches are rated about 15 amps each, but my power supply current limits at about 3 or 4. So actually, I don't put circuit breakers or fuses. I just rely on the power supply just shutting down if I get a short circuit, and it doesn't take out any of the I/O boards. They self-regulate. So coming back to Richard's question, you not only just worry about having enough current rating in the power supplies. I deliberately don't I don't overrate them either, so I can actually use the current limit function in the power supply as my protection.
Yeah.
But remember, when you've got one of these switch mode, like John was saying, you got 5 volts out, and say it's 5 volts out at 1 amp, and you put 10 volts in, it'll be half an amp in. So your 24 volt supply is going to be, like a quarter or something like that, a fifth of the load current. So if the Pi is drawing an amp, the 24 volt supply is providing 200 milliamps or something like that. So that's where these buck regulators have got a real advantage.
Yeah, thanks for that.
Richard, I've bought quite a few of these, and pretty much the only problem I've had with them is when the output current, which is what they're rated on, doesn't live up to the promises. And that's something you can find out pretty quickly just by loading it up when you first get it. As for choosing a design that'll do more than about 5 or 6 amps, that's quite tough. I haven't found, I found 1 or 2 that'll do 10 and 12 amps easily, but for me, it's been a guessing game, or try it and see.
Yeah, I guess the question is whether or not you can trust some of these suppliers or these manufacturers.
Yeah.
Well, they all copy the same spec.
So here's a circuit board. So you can see a Pi on the bottom and a stack of I/O boards. And on the top, see the power supply there? So I do is I bring in 24 volts here through a Phoenix connector. And I'm actually feeding this stack of I/O boards and the Pi through the ribbon cable. So I've probably got 200 millimeters of ribbon cable tucked underneath it. I can see it. Yeah. So the power supply is on the top. I daisy chain down through my IO boards to the Pi, and that works quite well. So that's one reason I adjust the power supply up for another 100 millivolts or so to account for voltage drop in the ribbon cable.
Nice. And sorry, you're also saying that you connect directly to the GPIO to provide the power to the Pi.
Yeah, you can see here. I'm not powering the Pi through that connector at all. I'm coming in through the ribbon cable.
And there's no practical concerns with doing that. It doesn't bypass anything on the Pi, any protection or anything you worry about.
Well, I don't worry about the fuse on the Pi. I've got protection up here in this thing.
That makes for a very neat assembly.
Yeah, so that's really good if you've got like a small case and you don't really want to. You don't have a separate USB. Sometimes those really small plastic cases, you have trouble getting the USB in nicely. It's better to go by the GPIO.
So I take my field wiring in through a DB25 connector. So I've got an 8 input and 8 output board. So this thing, so it's as simple as 8 in, 8 out, opto-coupled with I2C on the bottom. So I talk to this board. I just daisy chain these up.
Wow, that looks really clean. I like it.
So
puts our amateur versions to shame.
Yes.
The last batch of these, I built 100 of these.
Well, not all yourself, I hope.
I started.
Yeah.
Co-opted others into. I mean, these are in a factory, so we've got people in the factory can help me do that.
Yeah.
Very cool. Any other questions for Tony? It was a pretty in-depth session. 2 in-depth presentations.
Actually, just something that John was doing earlier with the temperature rise on the cables, etc. Just a couple of comments because we make as a day job, I make cable, I extrude cables and etc. So things like PVC insulation, etc. Typically, you don't want to take the copper above 75 degrees C. That's the top limit for insulation. If you're in the fluoropolymer, DuPont call it Teflon, but there's a stack of others. You can go up to 150 C for that. But the real limit is the connectors. Quite often the limit for a connector is a 45 degrees C rise above ambient. So that's typically where you'll say that's where, and that's the limit of a connector, by the way. It's not the design point. So that's typically in my mind where I'd be limiting temperature rise would be, I'd be limiting at something like say 30-degree rise, absolute maximum. Otherwise your connectors will. What will happen is on a cyclic load, the connectors will fail after a while. They'll go high resistance.
Well, yeah, I mean, one of the things that I realized with that piece of wire, I mean, I wouldn't recommend putting 5 amps through a piece of wire wrap wire. But one of the things I realized was I've sort of said that there's 1 watt being dissipated across the length of the wire. Well, if you flexed one bit of that wire more than the rest of the wire, then that's the bit that's going to heat up, and because it's going to have higher resistance.
Yeah.
So, it's not an exact science, but I, from that little experiment, I did, to start with, I was a bit nervous about doing it because I thought it's going to be sort of loads of smoke coming off this, but now I kind of realized if I'd gone up to about 7 amps, I think that piece of wire would have sort of really started smoking, and because every time you go up, every time you double the current, you quadruple the power, and so you quadruple the temperature. So
It would be interesting explaining that to the insurance company when you've had a loft fire.
yeah,
We want to be a bit vague in what you're doing.
it was, it was interesting. When I was doing all these measurements, I was working things out to sort of milliohms. And before I would have kind of thought, yeah, a milliohm, who cares if it's sort of 10 milliohms or 20 milliohms. But actually that makes a big difference when you're dealing in sort of 5 or 10 amps.
Yeah.
What will actually be interesting is because I do this a lot, is doing high current testing. You'd be surprised how warm your house wiring will get if you're drawing, say, 15, 20 amps out of an outlet. What the temperature rise of the cable in the wall is actually it can be 20 or 30 degrees rise easy. You just don't experience it because you never.
Yeah, no, I did sort of measure. I measured various bits of wire. I had a 20-meter extension lead that said it was capable of doing 13 amps, and I measured that to be sort of 30 milliohms, I think it was, over the entire 20-meter length of the cable, which I still think is pretty good, but it does mean that if you were running something at 2 kilowatts, you'd be losing about 100 watts in the cable reel. And they do say that you should have the thing fully unraveled.
Yes.
And I can kind of see why, because you don't really want 100 watts dissipated in something that's all cabled up, all coiled up.
I've had one melt together, and when I've measured them, I think they've been nearer about 0.9 ohms, something like that. Silicone wire. Silicone insulation is sometimes specified as surviving at 200 degrees, but you see some silicone wire advertised a lot cheaper than others. Is there any way to tell what's the real stuff?
One way to do it is because we don't make silicon, but we've got it. It's quite a complex. It's quite a brittle material, so it actually will just peel off and fall off the wire if it's cheap. Anybody that's reputable in silicon, because it's such a specialised wire, will probably go and have an American UL rating on it. And UL as an insurer protects their brand name by actually doing spot checks. So they turn up to us 4 times a year and roll into our warehouse and actually take a sample of wire and go away and test it. So while it's an American standard, they've got fairly strong protection behind them in terms of, if they quote it's got a UL certificate, you could use that as a first line of determining whether it's a reputable silicon or not.
That's great, thanks.
But you can take that up to about 200 again, like Teflon. You can take it up about 150 C.
Okay.
If you want to go higher, you use Pyotenax.
Yeah.
Mineral insulated copper sheet. Yeah.
But typically you're using these cables not because you're putting huge current through them, and you worry about temperature rise. It's the ambient, like it might be in an oven or something like that, which is something else creating the temperature.
Yeah.
And you're just protecting the cable from the ambient.
Well, this is for building a lithium battery. That's where you see it sold. The stuff I'm looking. Okay.
Yeah, and it's quite flexible too. It's unbelievably flexible.
Yeah.
I didn't catch that myself, but Catherine has asked someone who did put it in the chat before the conversation moves on, and we can't remember what she was asking for.
Yeah, I'm not sure what the context of that was.
Is that what about? Oh, okay.
About the certification.
Okay, so let me type it here. So I'll type it in the chat. It's the certification is UL, which is a US Underwriters Limited,